Let's talk about subsetSum, which is a problem that we're going to try to solve using our generic backtracking solver. To begin with, let's just look down here and look at what subsetSum is trying to do. Given a list of numbers, and there's a list of numbers, and given a target value, and there's a target value, the question is, can you find some numbers among this list that add up to that target value? And if so, return that list. So here, 3 plus 5 is 8, plus 7 is 15, and so the answer there is certainly yes. There could be other answers. Obviously, in this case, like 5 plus 7 plus that 3 would also work, but we just have to find one of them. Cool. To see how this works using backtracking, let's use this little example we made here, okay, which creates this app that we're going to look at, okay, and now, okay, great. So now what I want to do is I have a list of numbers and I have a target, and I want to find a sublist among that list that sums to that target, okay? And so what we have to do is we have to go through this list and we have to make moves. And so what we're going to do, a move here will be to include or not include, to use or skip the next number, okay? So we'll first try using it, and if using it doesn't work, we'll try skipping it, okay? If it's gray, it means we're neither using nor skipping. If it's green, we're using it. If it's pink, we're skipping it, okay? So we start out by trying to use the 3. Since we've made that move, we recursively try to now make moves over the rest of our values in the list. So the 3 is in our partial solution that we're building up, and from the 2 to the 1, those are our remaining values, okay? So then we try to use the 2, and we recurse again. We try to use the 8. So the problem now is that we have this constraint that in the end, we want to, of course, have the sum exactly equal our target. But as we're going, a good constraint is simply that it can't be larger than our target, because once we've done that, no matter what happens after that, we can't find the solution. Think about when we were placing the queens. When we placed 2 queens that attacked each other, there was no reason to continue, because no matter what happened after that, you couldn't find an answer. Same thing's true here. No matter what we do with the rest of this list, because our total is too large, we violated the constraints of the problem. So then we, at this level, we try the next move. So one move was to use, now the next move is to skip. Okay, so we keep going, we try to use, target's too large, so we try to skip. And then we keep going, we try to use, and we got to the end. Since we've run out, we either solved the problem or we didn't, and we didn't. So then we try to skip and fail. So now we backtrack, because the only things you could do are use or skip. Since those are the 2 moves, when you've exhausted all the moves, you backtrack to the previous level. Just like with the queen, when we placed it in every row for a column, at that point we go back a level. So back a level, back a level. Now we're going back a level, skip here, and we're going to play the game again. Oh, using was too large. Then we'll try to skip, use, and look at that. And now we found the answer, and we're done. And we would return the list 3, 4, which still is what we're calling our partial solution. But when the target equals the total, that becomes our actual solution. So this shows you how backtracking can be used to solve subsetSum. Let's now go take a look at the code in action, okay? So we'll go in here, and we'll copy, go up here, and we'll go to subsetSum, and we will copy this code, and we'll attempt to run it, and we will see when we do that it does not run, because state is not defined. But we sort of knew that. We said that we were extending the generic solution, so we need the backtracking puzzle solver class, and we need the state class, which we get by copying that code, put it above this code because it's using it, right there. Okay, and now I run it, and sure enough, it runs. So now let's take a look at what it does when it runs. By the way, it's still running for one more moment. Cool, so let's look. So sure enough, we had this list, and we had this target value, and it found the answer 357. The moves that it could use, make were either use or skip. So the first, when we first started, these were all our remaining values. Our partial solution had nothing in it, But then we decided to use the first value, which placed a 3 in our partial solutions and made this our remaining values. Our next move was to skip the 6. Our next move was to use the 5, skip the 2, skip the 11, and use the 7. And when we found this series of moves, we managed to get from this start state to this solution state. We detected it was a solution because 3 plus 5 plus 7 does equal 15, and we were done. We had to explore 29 total states and make 6 moves to do it. Sure enough, 1, 2, 3, 4, 5, 6 moves. Great. And it took, well, it wasn't instant, but it was less than a millisecond. Cool. We reran the exact same thing, only this time with check constraints false, which means that we are not checking the constraints as we go. In the n queens example, that's like when you put 2 queens next to each other, but then you just keep adding more queens. So this is just exhaustively searching the space, which required more states and more time, but still pretty darn fast. So after that, just to take a look at how much of a win we're getting out of backtracking, we have this example where we have n, and we'll create a list from 1 to n, and the target will be the sum of half of those numbers. Okay, and we'll go ahead and we'll solve it, and we'll solve it with using backtracking, and we'll solve it then without enforcing the constraints. And here is our list from 1 to 50. Okay, and our target value was 625. With backtracking, here's the moves we made. Here's the resulting list, which we assume does add to 625. And we required 1,176 states to be created, 50 moves, of course, and only 17 milliseconds. So it solved that very quickly. By contrast, when we turned off backtracking and solved the exact same problem, this time with constraints false, and we wind up with an answer. So we found an answer. That's great. But we required 524,000 states. Remember up here it was 1,100. So many times more states. And instead of 17 milliseconds, it's 7,300. So 7.3 seconds, quite a bit longer. And as n grows larger, this difference will only grow larger still. So what we're seeing is that in a lot of cases, the backtracking is dramatically faster. Okay. Now, there are worst cases where the two will be the same, but in general, backtracking can be an enormous win, as we've seen here. In the next part of the video, we will explore how to actually write this.